Okay, so welcome everyone for the live session for week 9 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur. I am Anant Singhal, a PhD student from IIT Jodhpur, and today I'll be assisting in solving some of the similar assignment problems that have been given to you in your week 9 assignments. So we have already reached like towards the last part of this course, and if I go towards the course outline, um, we have covered all the basics and the device physics that we have in three particular devices. And from the last to last week, we started some of the models or the theories that we have regarding the movement of electron in any semiconductor device. So in the previous week only, we started with the DD models that are the drift diffusion models that were already present there. So in the previous week, we did cover some part of the drift diffusion model, like we took some of the cases in which what we did is we covered the diffusion current density or the diffusion current derivation that we had that we missed before, and drift current we already had some derivation before. So that was some of the basics of the drift diffusion model. And as you can see in this particular week also, we'll be continuing with the DD models. And in this week, we'll more or less focus upon the generation and recombination models. We did cover some of them in the previous class, that is the impactination, that is the auger recombination model, and the direct band-to-band generation. Then there are one or two more recombination models that we'll cover in this particular class. And apart from that, there is this continuity equation that basically is a solution or is a differential equation that has been solved using this drift diffusion model. So we'll also cover the derivation of the continuity equation. And yeah, so as you can see, there are some of the iteration methods like Newton, Raphson, etc. So these are all application-based topics. So we'll cover some of the questions related to them, and then particularly move ahead. So if I try to quickly recall the previous class, so we started with the recombination and generation. Not started, but yeah, we started with this topic in the mid of the previous class. Uh, and then let's say, we took an example in which, let's say, we had a device or a bar or semiconductor which has certain recombination generation, and the flux was continuous. So let's say uh, some electrons are going through it, some are recombining, some are generating, and some are coming out of this. So yeah, I mean, these are some of the things, and we studied that for electrons, this change in concentration with respect to time could be due to, so let's say this is the total, and it could be due to the change in current, that is due to the flow of electrons. And then there was one more part that we more focus on is the recombination generation, and then we said there could be any other process also, but we are not very keen on going towards any other process. Similarly, for holes, we did that dn by d, sorry, not n, it should be p. So the total could be due to, again, it could be due to the current, it could be due to the recombination generation, and any other process. So we are not very keen on any other process because these are the two main things that we want to be focused on. So, and then we establish that we know that at thermal equilibrium, what do we have? The total current component or the total change needs to be zero. So for electrons, we established that dN by dt should be zero, but that doesn't mean that at thermal equilibrium, the individual component, okay, for equilibrium case, it would be zero. So let's say the current will be also zero and the dN by dt should be also zero. But we are only talking about equilibrium. Similarly, for holes, if we replace this n by p, so it will be for holes. But the main concern was if we move out of equilibrium. So we have to be concerned when we are out of equilibrium. So for that, we need to have certain assumption or the theories in our mind. One is a steady state condition. Steady state condition is nothing but it says that the overall current component, because we are reached in the steady state, so the total current component will be always zero. But this doesn't mean that individual components could not be zero. So individual components may not equals to zero, but the total component will always be equals to zero in steady state because we have reached a steady state. That means there is no change in any concentration with respect to time since we have reached towards a stable state. So this is what we had in our basics, that at steady state we have dn by dt total that I have already written. This should be 0, and dn by dt current, or let's say even dn by dt due to recombination or generation, are not equals to 0. Similarly, the same will go for holes also. So yeah, if this is 0, and let's say I'm only focusing, since the topic says that we are only mainly focused upon the recombination and generation rate. So I'll even ignore this for now. And let's say dn by dt total is equals to 0 is what I have written. And this will be equals to only the recombination generation component, which will be nothing but generation rate minus the recombination rate for electrons. So again, it should be for the excess electron hole pairs that are being generated and recombined. So if I go with this formula, so the generation rate for this case will always be equal to the recombination rate. Similarly, for holes, it would be the generation rate of excess holes will always be equal to the recombination rate of excess holes. So if I try to summarize this particular thing, at steady state, what happens is, let me write at steady state, generation rate of excess carriers is equal to the recombination rate of excess carriers. So this is the main thing that we need to keep in our mind while doing the derivation, that the generation rate and the recombination rate will be equal in steady state. So yeah, so with that, if I try to have some more explanation of this, we establish that the total n would be, so for n naught plus the excess carriers delta n. Similarly for p, it would be p naught plus excess carriers delta p. Now, more or less what we are focused upon is the low level injection that we studied in the previous class. We say that our excess carriers are not as high as the majority carrier concentration. That means delta N and delta V should be very, very less than N naught for an anti-semiconductor, because N type is N naught is a majority. Similarly, for delta P and delta N should be very, very less than P naught for a P type semiconductor. So this assumption is nothing but low level injection. So LLI is what we call it that in general. And the recombination is always, I also told in the last class that the recombination rate is always focused on the minority carriers, not majority. So for example, it would be delta n, that is the excess carriers by the time. And now since we are talking about n, so this will be for p type. This is delta p by tau p, which would be for n type. So why I mean the minority carriers? Because that is the only thing that is actually changing. So I gave an example in the last class. So let me quickly try to give it again. So one thing is here, tau n and tau p are minority lifetime carriers. Minority carrier lifetime. So now if I try to give that example again, so let's say we have N naught, which is 10 to the power 15. We have P naught, which is 10 to the power 5. That makes this semiconductor as a N-type semiconductor. So in this, the minority will be holes, right? So now if I try to calculate, so let's say if I have delta N, or let's say I'll write the delta as it is. And delta V, let's say I inject only 10 to the power 5, which is what I'm calling as low level injection. Why? Because the delta N and delta P are actually very, very less than N naught. So if you try to calculate the overall N concentration, it will be 10 to the power 15 plus delta N, which is 10 to the power 5, which is approximately equal to 10 to the power 15. That means there is no change in the majority. But again, if I try to calculate the minority, which will be 10 to the power 5 plus, so this is P naught and delta N, and this will become twice. So the only main change that happens in any semiconductor is in the minority carrier concentration. So that is why in terms of recombination generation, we are only focused on the minority carrier concentration. So we'll be taking all these special cases in the subsequent derivations. So before this, we want to have the basic understanding of the continuity equation that I already told that it is one of the important topics. So let's try to understand what exactly is continuity equation. So this I didn't start in the previous class because this is a long derivation. It would have taken a lot of time. So let's try to have some understanding of the continuity equation. Yeah. So let's say we have a current flowing out in this particular box. Let's say this is having just dx length. So let's say this is at a particular x and this will be position at x plus dx, and the outflow of this will be around Jn at x plus dx. So x plus dx is the position and Jn is nothing but the current density. It could be the diffusion or it could be the drift. So we'll consider both. So drift and diffusion both we'll consider. And now we'll see what is the actual recombination generation rate. So let's say the cross section area of this, sorry, is A. So what will be the volume of this box? Can anyone tell? So the cross sectional area is A and the length is dx. What will be the volume? It would be nothing but area into the side that we have, A dot dx, right? Multiplied by dx. So yeah, so let's establish something. So let's say I'm talking about the rate at which, so I'm doing it in terms of electrons as of now. You can do the same with respect to holes and you will get the same result. So I'm asking the rate at which the electrons are entering here. So rate, we know that charge is the flow of current, which is nothing but current divided by time, right? So rate, it is nothing but current, that is the current density multiplied by the area, that will give you the current. So at which entering means at x. So at this point, the position is x. So Jn at x times area is nothing but the actual current, and the rate of charge will be nothing but, so time, if I try to write, is, let's say it's minus q because of the negative electrons. So similarly, what I can write is rate at which electrons are leaving the sample. So nothing will change, only the position will change, right? So it will be Jn at x plus dx. Area will remain same and the charges are also negative because it's still the electrons. Then further it's rate at which the electrons are generated. So since we are talking about the normalized, it will be Gn times the volume, which will be A dot dx, which we have already established. And at the last, it would be rate at which electrons are recombined. So it would be nothing but Rn A dot dx. So yeah, so we have been talking like for from a big time now that dn by dt total is nothing but, it could be due to current, which we have just written the rate of electrons, and it could be due to recombination generation. So let's say these are the two major things that we are interested in. So yeah, if I try to have the volumetric analysis, so I'm multiplying by A dot dx at both the sides just to have the volumetric analysis. So the change in current would be nothing but the entering electron minus the leaving electron. So I'll just write this, which is Jn at x times A dot minus q minus Jn at x plus dx multiplied by A dot minus q. So this is due to the change in current and the plus the generation minus recombination. So generation was A dot dx minus Rn A dot dx. So we just need to solve these things. So we have x dot dx. So dx is very small, right? So we can, what we can apply is, we can apply the Taylor series expansion that we studied in the previous class. So if I apply the Taylor series expansion, so using Taylor series expansion, so what we can write for Jn at x plus dx, so this dx is nothing but a, which is very very close to 0. So it is nothing but Jn at x plus Jn dash, that is dJn at x by dx times factorial 1, right? So factorial 1 here, it will be 8 dot, so dx by factorial 1. So I'm not writing 1. and I am ignoring the other terms. So this would be the Jn at x plus dx, the Taylor series expansion. So I'll put this in equation. Let's say I'm marking this as 1 in equation 1. So we'll have dn by dt total a dot ds because it is volumized. So the first term was Jn at x, area by minus q minus. So Jn at plus x would be now this Jn at x plus Jn, sorry, djn x over dx times dx. And again, so let's just keep this as constant, I mean outside the bracket, because a by q is everywhere. So minus a by q, let's keep it like that. Sorry, a by minus q. And then the second term is still the same, gn minus rn a dot dx. So using this, what has happened is we are being able to cancel the jnx, right? So yeah, if I try to now write it more, it would be dn by dt a dot dx. It would be a by q. Minus and minus will cancel out. Then it would be djnx over dx into dx plus gn minus rn a dot dx. So you see a dot dx is common in all these three terms. So I'll just remove that. So this will give me dn by dt is nothing but 1 by q djnx by dx plus gn minus rn. So this is some kind of short form of the continuity equation that we always see and that we always solve. So now, as I said, there are both drift and diffusion component. So can anyone tell what will be the Jn for drift and diffusion if there are both of the terms for electrons? What will be the Jnx? Can anyone tell? For drift it would be what? So it would be nq mu n e for drift, and for diffusion it would be nothing but q dn over dx. So this is the derivation that we did in the last class, right? So now what we'll do is we'll differentiate it so that we can put it here. So I'll take this q in the LHS, it will become 1 by q, and I'll differentiate with respect to jn over dx. So now there are two terms that are changing with the position. That is, one is the concentration, one is the electric field. So we'll apply the product rule. So let's say n mu n is kept constant. So the first term would be d by dx. Then mu n e is the second term, and the second term would be dn by dx. And this will be nothing but the second order differentiation. So it will be dn d2nx over dx2. So let's say this is equation 2. Now put this in equation 2. So using this, what we'll get is, so I'll just write these terms here. So it will give me that overall dn by dt is equals to, will give me the overall dn by dt, that is, so the first term is 1 by q. So I'll just write these three terms, mu n e dn over dx plus n mu n d over dx plus dn d2n over dx2 plus gn minus r. So this is nothing but the continuity equation for electrons. Here I am talking about excess carriers, so we'll again are focusing on the minority carriers. We need to always remember that. So this will be used for the any p-type semiconductor in which your n will be nothing but n naught plus delta n. That is, delta n is the excess carriers. So similarly, you can do the same for holes. So if I try to like write in very basic terms, so for holes, so I'll not write or do the derivation again. So again, let's say we had some semiconductor in which the JPX was the inbuilt and JPX plus DX was the outgoing electron, sorry, now the holes. and again it was dx. So we could have written directly using dp by dt total. It would be nothing but jp x a by q. So a plus q because we have holes. Then it was jp x plus dx a by q. Again this is holes plus again gp minus rp a dot dx. And using this, what we would have done is we would have again used the dp by dt and the Taylor series expansion, which we have cancelled this term, and it would have led to 1 by q djp by dx plus gp minus rp. So this is again the short form of the continuity equation, and then we would have again gp is nothing but we know it's p cube mu pe minus q dp by dx. So if we would have again differentiated and did the same thing, we would have got the final continuity equation. So you can do it in your home also. That is p mu p dE over dx minus p mu pe dp over dx and plus dp d2p over dx2 plus gp minus rp. So now this is what? This is the continuity equation for holes. Again, these are the excess carriers you need to remember when we are solving anything. So P is nothing but P naught plus delta P. So this is what we are solving because this is constant. So what I'm trying to say is if I do the dP by dt, it will be 0 plus d del P by dt. So this is what we are more or less focused on. So yeah, this is what we have the continuity equation, and using this continuity equation, we'll now solve those three cases which we are talking about from the previous class. One is the steady state, one is the low level injection, and last is the there is no generation recombination. So yeah, let's go do that now. Okay, so I'll start again. We are more or less focused upon the minority carriers, and that too with low level injection. So we'll always be talking about low level injection, high level because we in general don't do. So there are few assumptions or approximations that we always take. So the first assumption or the approximation is that there is no electric field in any of the samples. So this means E is 0. The second assumption that we take is equilibrium concentration do not change. That is the N naught and P naught are constant. Then the third assumption that we take is, as I've written, low level injection. So using these three, we'll try to take those three cases. So let's say I'm talking about a n-type semiconductor. So which continuity equation I should solve? Because we are talking about n-type semiconductor. Should it be N or P? Any guesses? So n-type semiconductor, right? So we are only interested in minority carriers. So minority carriers will be nothing but P only. So again, so the P will be P naught plus delta P. That means your dP by dt will be 0 because your equilibrium concentration do not change. Then it would be d del P over dt. And then there are few more assumptions that have been given in the question. That is the electric field is 0 and there is low level injection. So yeah, first of all, if I try to write, so second thing I'll write electric field is 0. So if I try to write the equation which we have just established, that is dP by dt, so I'll write in del P because we have already reached. So now what is the thing is so electric field is 0. That means your this term will become 0, right? Because your electric field is 0. This will be also 0 and this will be also 0. So if E is 0, then dE by dx will be 0. So we are only left with that second differentiation and the Gp minus Rp. So I'll write that. So it would be dP d2. Now P we will replace with del P plus Gp minus Rp is nothing but, we have just seen in the initial uh, class that it is nothing but del P minus tau P. So this is the case when your electric field is 0 and your electron concentration does not change, and this is called low level injection. So similarly, let's say I can do the same for P type semiconductor. Let's suppose we have P type semiconductor. So we'll have the same thing. Your delta N will be very very less than P naught, and then your D, you solve it, it will come out to be the same thing. It will come out to be Dn. It will come out to be D2 del N over dx2 plus Gn minus Rn is nothing but del N over tau. So this will be the two things that we'll be starting for all the three cases. So the first case that we'll be studying is, so I'll write them as the special cases. So special case one is nothing but, let's say we are talking about steady state and there is no generation, that is there is no light. So what this will mean is your Gn is 0 and your dn by dt total is always also 0 because we are talking about steady state. So using these two things, if I just see this equation in terms of n, so your this term will be becoming 0 and your this term will be becoming 0, right? So if I write that, it will be 0 d2 del n over dx2 plus 0 minus del n over tau. So again, this is kind of a double differential equation. It is nothing but, let's say if I replace del n, so it will be dn del n over dx2 is equals to del n over tau. So if you consider del n is, let's say y, so it is something a d2y by dx2 is equals to y by some constant b. So this is our directly solvable second order differential equation, and the solution to this equation is nothing but, so del n comes out to be okay. So one thing is this dn is here, so I'll just write dn here, and this we have established that this is nothing but ln, which is the what do we call it? This is what we call as the diffusion length. So I can write, let me write one more step here. So it is d2 del n over dx2 is nothing but del n by L square or ln square. So now if you solve it, your final solution comes out to be some a ex by ln plus b exponential by ln. So this is the general solution of the case when we have steady state and we have no light. And here a and b are constant that we can find using some of the things that are given in the question, that is a boundary condition. So we'll be doing some of the questions that you will be seeing that how we can find this a and b. So this is the special case one that we had. Now if I try to go towards special case 2, in which what do we have? We have no concentration gradient and still no light. So we don't have steady state right now, but we don't have any concentration gradient. That means still the Gn is 0 and your dn by dx is also 0. So this is your special case 2 that we have. So if I again write the concentration gradient, we know that dn by dx is 0. That means your d del n by dx will also be 0. So if I try to write the final equation, so this was d del n by dt. So actual equation was d2 del n over dx2 plus gn minus rn. So this will become 0 and this will become 0 based upon the case that we have taken. So this will be nothing but d del n over dt is minus del n over tau n. So this is a very easy first order differential equation, which is just the exponential relation. So the solution to this, I hope you already know this. So del n is nothing but, let's say, delta n naught, that means at some constant exponential of minus t by tau n. So this is the general solution for the case 2, when we don't have any concentration gradient and when we don't have any light. Now there is last case that is remaining, which is very easy actually, because we'll take the two main things 0. So again I'll write special case 3. So in this case, what do we have is, we also have steady state and there is no concentration gradient. But this time what do we have? We have light. So in this, dn by dt is also 0 and your dn by dx is also 0. Right? So this will make your equation 0 is a LHS, then d2n by dx2 will also be 0 plus gn minus Rn. Rn is del n by tau. So using this, your del n is directly Gn times tau. So this is the general solution for case 3, when we don't have when we have the steady state and we don't have the concentration gradient. So studied three special cases. The first one was when we have steady state and no light, using which we had the general solution. The second case was when there is no concentration gradient and no light. For that, the general solution was this. And the third case was when we have steady state and no concentration gradient. For that, the solution was this. So we'll do one numerical for all these three cases. So let's quickly try to cover that. Okay. So let's see which case we are talking. So let's say I'm talking about a p-type semiconductor. So what solution are we going towards? If we are talking towards the p-type semiconductor, then the minority carriers, right? So we are only focused upon the dn by dt. So let's say we have a p-type semiconductor which is doped with 10 raised to power 15 per centimeter cube. Then we have 300 Kelvin temperature. And let's say the electric field of that particular semiconductor is 0. And what do we have? Let's say there is no light entering at x is equals to 0. And this semiconductor has a length x. And what has been given that at s is equals to 0, your concentration gradient or the excess carrier concentration is nothing but it is given as 10 to the power 13 per centimeter cube. And your mu n is given as 1200 per centimeter cube, centimeter square per volt second. Sorry. The mu p is given as 400 centimeter square per volt second. Then your tau n is 5 10 to the power minus 7 seconds. Tau p is, let's say, 1 10 to the power minus 7 seconds. So now the question is, find the electron diffusion current density at steady state. So now you need to just focus on two words in this problem, that there is no light. So I've said that there is no light, but I have not written. And there is steady state. So which special case should we solve? Anyone? We already had a general solution to this special case. So do you want to solve it? So we have no light in steady state, which is nothing but your special case 1, right? When we have steady state and no light. So the general solution is this. So we need to solve for A and B, and that will be our final answer. So let me do it for now, and you can do the easier one, which is the next case. So yeah, if I try to do the solution. So as I said, what do we have? We have steady state and we have zero electric field, or we have no light. What does it mean? That your dn by dt is 0. So just to simplify things, I'll write all the things. So it would be n mu n dE by dx plus mu e dn by dx plus dn d2n by dx2 plus gn minus rn. So as I said, steady state is 0, electric field 0, so these two are 0. So the first case and the light is 0, right? So using this, we just established 5 minutes ago that your del 2 n by del 2 del n by dx2 is nothing but del n by L square, where L was under root dn tau n. And we reached towards the general solution, which was a exponential of minus x by ln plus b exponential of x by ln. So now what is there? So we need to put the boundary condition. So let's say if I took at x is equals to infinity, we know that there is no excess carriers at x equals to infinity. There are only excess carriers that are present inside the sample. So if I try to put this condition, so what will be 0? Can anyone tell? Is it A or is it B? There will be one term which will become 0 because at x is equals to infinity or del n needs to be 0. A will be 0 or B will be 0. Can anyone tell? So your del n is 0 when your, so this will be minus infinity plus b exponential of infinity. So since this is multiplied by infinity, right? So we need to make b is equals to 0. That means your equation has now been written to del n x will be ax minus ln. Now there is one more thing that we also already know that del n at 0 is 10 to the power 13 per centimeter cube, which is already given in the question here. So what we can do is del n at 0 will be 10 to the power 13 into, oh sorry, so it would be a times exponential of 0. So this will give your a to be 10 to the power 13. So the final solution for del n x, it will be nothing but del n naught, which is 10 to the power 13 exponential of minus x by ln. So now ln we also need to calculate because it is given in the question. It is dn times tau n. So dn was 31.2, which I already gave. Then your time for time constant for n is 5 into 10 to the power minus 7. And if you solve it, this will come out to be 3.94 10 to the power minus 3 centimeter. So now the question is asked you to calculate the electron diffusion current density. Electron diffusion current density, that means Jn diffusion, right? So Jn diffusion is nothing but Q dn over dx. So we already have our delta n with us. This is nothing but excess carrier. It would be d del n by dx. So if I put that, it would be Q is nothing but charge. Dn is 31.2. And then the differentiation of this del n. So there is Q dn. So the differentiation of this would be, where is this? This would be 10 to the power 13 into minus 1 by ln, right? And then exponential of minus x by ln. So ln we have just calculated. So let me try. So minus 1.6 10 to the power minus 19, 31.2 into 10 to the power 13. ln was 3.94 10 to the power minus 3. Exponential of minus x by ln, I'll again write minus 13. Okay, so if you do some maths, this is 16 minus 3. So something milliamps per centimeter square, I'll write. So it's 10 around, I think 12 or something, it will come out. So minus 12.67 is what it is coming out. Exponential of minus x by 3.94 milli. So this is your diffusion current density. So this is what has been asked in the question. So since it is not asked at any x value, so we need to have a variable answer. So is there any doubt in this particular problem? So this was a case one that we studied before. So is there any doubt? If not, let's move towards the next case. Which is, let's say, if you will able to figure out or not which case is this. So now your next problem is, let's say we again have a silicon which is at room temperature. Okay, we have n-type silicon. Let's say your doping is given by 10 per 5 into 10 per 17 per centimeter cube, and your excess carriers are 10 per 14 electron hole pairs. So that means your del n and del p are this much. Your GP is 0, that means there is no light. NIL gave you, and your tau p, because minority carrier lifetime is what is required, ns, nanosecond. So the question is asking the time at which minority carrier hole concentration reaches 10% of its initial value. So this is what has been asked. So again, as I said in this question, what has been given? There is no light, first of all. And the second thing that has been given in this question is there is no concentration gradient. So this is nothing but your case 2, right? So this is a easier one. Do you want to solve this one? So case 2 was nothing but this. When we had, yeah, this one. When we have no concentration gradient and no light. So general solution is just this. You just need this equation to be solved, and then you'll be able to find the time 10% of the initial concentration. Maybe give 2-3 minutes to this, and if you're not able to solve it, I'll solve it by myself. Okay, so let's try to solve this now if you don't have any solution. So as I said, in this question, what do we have? There is no concentration gradient and no light. So again, if I try to write from starting, so it is nothing but dp by dt is nothing but mu p e d p by dx plus mu p d e by dx. Yes, plus dp d2p by dx2 plus dp minus rp, which is del p by tau p. So since there is no concentration gradient, this would be zero. Then dp by dx, so p will be zero. So we have already established these things. That your these four things will be zero, and your dp by dt comes out to be minus rp, which is minus del p by tau p. And the basic solution to this is, so this is nothing but equivalent to dy by dx is nothing but y by some constant a. So 1 by y is the solution of log. So your del p will come out to be del p naught exponential of minus t by tau p. So this we have already seen, I mean, in the derivation. So now the question has been asking that the time at which the minority carrier hole concentration, that is del P, reaches 10% of its initial value. That means initial value is, let's say, del P naught. So it is asking the time which is at 10% of this initial value, right? So what is that time? So first of all, the initial value is nothing but 10 to the power 14, which is given in the question, exponential of minus t by tau p. So let's say the time is t1 at which it is at 10%. So your del p will be 10% of del p naught, which is 10 to the power 13. So yeah, I mean 10 to the power 13. So what I'm trying to say is del p naught exponential at minus t1 by tau p is nothing but 10 to the power 13. So this we already know, it's 10 to the power 14. So this will be cancelled and it will be around exponential of minus t1 by tau p is zero point 0.1. And again, if we take log at both the sides, so ln at 0.1 will be minus t1 by tau p. So tau p is already given in the question if I'm not wrong, is it? Yeah, it's 50 nanoseconds. So your t1 is that time at which it reaches the 10%, so it will be minus, so minus will get cancelled by 0.1, so it will be 3.0303 times tau p only. So your t1 will come out to with 2.303 into 50 nanoseconds. So the time at which the concentration becomes 10% of the initial concentration is this, which is 23, 5, 3, 15, 5, 3, 15, 5, 3, 15, 11. So it is 115.15 nanoseconds. Let me write it clearly. So at this particular time, your initial concentration, or the sorry, your minority concentration becomes 10 times of your initial concentration. So this is the special case 2 that we have covered. So special case 1 was a longer one, 2 was easier one, and the third is very direct, so we don't need to solve it. So let's say we have some generation rate that is given in the question and the time lifetime, then we can directly calculate the excess carriers using this del n is equals to gn into tau n. So we are not solving it. This is pretty straightforward. So there is one more recombination generation that was not covered in the previous class, which was recombination generation through exciton. Let me quickly cover that. So there is one more recombination generation which is which happens through, there's a special particle which we call as exciton. It's exciton. So let's say this is ECEV. So we already read about direct to direct, band to band direct recombination generation and the Auger recombination in the previous class. So there is one more which is the exciton. So let me tell you what is exciton. So let's say this is your EV which is filled with electrons, and we apply certain energy which is due to which there is a hole here, and this electron starts to go from here to your conduction band, right? So what happens is if you apply the energy more than that of Eg, right? If you apply the energy more than that of Eg, it would become direct band to band recombination or generation, sorry for this case. But if you apply the energy which is less than that of Eg, but equals to also. So what happens is this hole and this electron becomes interactive to each other. So till the time that you will not apply the energy which is greater than that of Eg, it will not go above, right? So if you apply, let's say, energy which is very close to that of the band gap, so there is this particle that we have that the hole is always being associated towards the to the electron. So this particle is what we call as exciton. So in this particular case, when you apply the energy which is very close to that of the band gap, is what we call as the generation using exciton. So exciton is nothing but electron and hole which are free, that is, they are not bound, but they are coupled to each other. And what they do is they diffuse together. So let me write it again quickly. So this is the exciton that I was talking about. That is, we apply the direct greater than Eg, it is direct band to band. And if it is less than equals to that of Eg, we have exciton. Exciton is nothing but the electron and hole which is free but coupled to each other. That means they diffuse and move through the semiconductor. So this coupled behavior is what we call as exciton, and using this whenever the generation or the recombination is the same. So let's say this electron is coming back and it is coming back in terms of an electron and a hole pair, which is something like here. So this should would be recombination. So again, we know that what is generation recombination, it's just the opposite process. So if it happens in terms of an exciton, that is, they are both electron and hole which are coupled and that are helping in your recombination generation is what we call as recombination generation through exciton. So for that, there is this problem which says in case of the band-to-band recombination, how increasing doping concentration. Sorry, this is not the problem. Let me go towards the problem if there is any. So yeah, so this is a question which says which recombination mechanism involves the combination of electron and holes bound together. So agar recombination is due to impact ionization, there is no boundation. Then exciton recombination is the answer because we have the electron and hole bound together. Shallow level is not, and these two are out of scope. So exciton recombination is also a part of the syllabus, which I have like tried to cover in a very layman language. So after that, what do we have is yes. Is there any doubt? Am I audible? Hello. Okay. So I'm hoping not. So let's try to do this question. So it says calculate the recombination rate. So you can ignore SRH because that is just to confuse you. So it says calculate the recombination rate of an N-type semiconductor. So we have an N-type semiconductor with excess hole concentration of 10 to the power 19 and the minority lifetime of 2 microseconds. So N-type, the excess carriers would be holes because these are minority. So del P is also given and your tau P is also given, which is 2 microseconds. This is a straightforward question. Let me know the answer in the chat box quickly. Take 2 minutes and let me know the answer. This is straightforward. So I've got one answer which is option C. Let's see if it is correct. So again the recombination rate would be nothing but del P by tau P. So del P stands for 19, which is given in per meter cube, and tau P is 2 microseconds. So the options are in both meter and centimeter. So 19 meter. So yeah, all are 19, so we need to convert them into centimeter then. So this should be minus 6 centimeter cube per second. So this will be 2 into 10 raised to power minus 6. This will get cancelled out. So this will be 0.5 times 10 to the 19 centimeter cube per second, which is option C. Yeah, option C is the correct answer. So let's move ahead. It says given an n-type semiconductor with a capture coefficient. Okay, so this is again a formula based question. So capture coefficient is given in the question, which is stands for minus 14 meter cube per second. Trap density is also given, which is 2 times per 14 per centimeter cube. We need to find out tau p. So this is again a formula based question. So let me write the formula. So tau p is given by 1 by capture coefficient times your trap density. So you just need to solve this. So one is in meter, one is in centimeter. So you need to be closely seeing that. So yeah, so either make the meter one in centimeter or the centimeter one in meter. And quickly let me know the answers in the chat box. So again take 2 minutes and let me know the answer. Yes, I've got one answer which is option A. So let me make this in centimeter itself. So it should be plus 6. So this is meter. This will be cancelled. So yeah, it would be half. Sorry. So yeah, it would be half into 10 to the minus 6. That is 0.5 microseconds. So option is the correct answer. Okay, let's move ahead. So it says calculate the absorption coefficient of, okay, absorption coefficient. So this is again I think next week's topic, which is optical absorption, which is basically given by I is equals to I naught. So I'll be explaining this topic in detail in the maybe next to next class, whenever this topic is mentioned in the syllabus. So I think we can skip this for now. Okay, so we have one more recombination question. It says given uniform illumination with light, that means the generation is there, which is given by this value in a p-type semiconductor. So that means the minority carriers will be n-type. So it is asking what is the distance between the electron quasi-Fermi level and the intrinsic Fermi level. So EF minus EI is what it is asking, and it is given that intrinsic carrier concentration is this, your minority lifetime is this, and it is at room temperature. So this is actually a good question. So yeah, do let me know the answer in the chat box. So this is again very straightforward. You need to just calculate the excess carrier concentration using the generation rate, and that will be your equivalent doping for the minority carriers. And using that, you can easily find out EF minus EI. So take 2 minutes and let me know the answers in the chat box. Okay, so there is still no answer. This is straightforward. Okay, so let me do it. So since this is an N-type semiconductor, sorry, this is a P-type semiconductor. So your excess carrier is given. So it would be for N. It would be transfer 20 per second. So now your del N, which will be your excess carrier, is nothing but G and tau N. So it is transfer 20 and tau N is given as 1 micro. So that means your uh, excess carriers are 10 to the 14 per centimeter cube. So EF minus EI is now nothing but straightforward, right? It is what? VTLN. Since we are talking about minority carriers, so ND will be replaced by del N over Ni. So you have everything given in the question: 0.026 ln. Del N is transfer 14 and Ni is given, right? Yeah, transfer 10. So it's nothing but 0.026 ln 10 is per 4, which is 0.026 times 4 times 2.303 electron volt. 0.20. So it will come out to be something 0.2, I guess. Is there any option like that? Yeah. Oh, there is 2, 1 and 2, 4. So yeah, it should be more than 3. So it should be 0.24 electron volt. The correct answer would be option C. Okay, so yeah, let me quickly uh, go through what we have done. So optical absorption we will be covering in the subsequent classes. So I'm not doing this numerical today. So yeah, so majorly what we have covered is we have covered most of the concepts upon the recombination and generation rate that is there in your syllabus. So there is one formula based question which was this capture coefficient, which we have also covered, which is nothing but the tau p is 1 by capture coefficient times the trap density. Then there were three main things that we have covered. So one is the exciton recombination, that we have seen the concept that how these excitons are forming and how does it actually happens. Then we mainly covered the three cases in which, let me go through there. So the first case that we had was when there was steady state and no light. So in this case, we have reached towards the general solution, that was this, which is the delta n is a function of exponential function of x by ln. Then the special case 2 that we studied, it was when there is no concentration gradient and no light. In this, your delta n was nothing but the function of exponential of minus time. And at last, we did the third case, which was steady state and there was no concentration gradient. And this was very straightforward. In this, the delta n was directly given by g and tau n. So it was not any exponential or any time dependent or the time dependent or the position dependent function. So yeah, these are the three special cases that you should be remembering for all the questions that you will be doing in your assignment 9. And then we also did the derivation for the continuity equation for both holes and electrons. So again, we need to be very clear that we will be doing this for minority carriers. So for any n-type semiconductor, you will be doing the same for dp by dt, that is the p-type semiconductor, and for p-type semiconductor, you will be doing it for n. So these are the few things that you need to be covering, and then this derivation that we did for the continuity equation is again important. And at start, we again started with some of the recombination generation, that is what is steady state. And so yeah, so more or less these are the drift diffusion models. So in the last lecture only, I've covered the diffusion model derivation. Drift we already covered in the initial classes. So this is more or less complete coverage of the drift and diffusion model. So I think if you don't have any doubt, we can wrap up the class for today and we'll meet the same time next week. And in the next week class, we will be seeing some of the extension of the drift diffusion models and some of the tunneling and all those, as I said, the optical absorption questions that we'll be covering in the subsequent classes. So if you don't have any doubts, I think we can wrap up the class for today. Um, so is there any doubt? Okay then. Thank you everyone for joining. So we'll meet next time, next week, same time. Yeah, till then, bye.